There is a moment, lasting roughly 200 milliseconds, where something stranger than most people realize happens inside a machine. You type a question, you hit enter, and before any word comes back to you, somewhere inside a data center the size of a city block, a mathematical object containing more than 1 trillion individual numbers rearranges itself in response to the specific pattern of your words. Not searches a database, not looks up an answer, rearranges. The output it produces does not exist anywhere before you ask. It is constructed, on the spot, from a landscape of numbers so vast that if you printed every single one on standard paper, the stack would reach the moon and come back twice. That is not a metaphor chosen for drama. It is the actual scale of what happens every time you ask an AI a question. Right now, in 2026, neural networks are not a curiosity sitting in research labs. They are embedded inside tools that hundreds of millions of people use every single day, making decisions about what information you see, what loans you qualify for, what medical images get flagged as dangerous, and what job applications survive the first round of screening. The World Cup is happening right now, and the broadcast system generating the real-time statistics you see during every messy goal is built on neural networks. The federal courts are currently debating voting rights legislation, and the natural language systems used to analyze and draft those legal arguments are built on neural networks. The CDC's contested COVID vaccine study that was blocked and then published in a top medical journal was peer-reviewed using automated summarization tools that run on the same underlying architecture. If you do not understand how these systems actually work at a mechanical level, you are making decisions about your own life in a world you fundamentally misread. 2 specific consequences are worth naming directly. The first is economic. Across law, medicine, finance, and software development, the tasks being automated are not the dumb ones. They are the expensive, high-skill ones that people spent a decade training to do. Goldman Sachs estimated in 2023 that 300 million jobs globally could be partially automated by systems built on transformer-based neural networks. That number has not shrunk. The second consequence is epistemic. When you do not know how a system generates answers, you cannot evaluate when it is wrong. And these systems are wrong in ways that are specific, patterned, and not random. Knowing the mechanism is not a technical luxury. It is basic self-defense. To understand what is actually happening, you need to go back to 1943. Warren McCulloch and Walter Pitts published a paper proposing that a neuron could be modeled mathematically as a simple switch that fires when its inputs cross a threshold. The idea was seductive, but mostly theoretical for decades. Then in 1986, Geoffrey Hinton, David Rumelhart, and Ronald Williams published the backpropagation algorithm, which gave researchers a practical method for training networks of these artificial neurons. Even then, the systems were small, brittle, and computationally expensive. For nearly 20 years, neural networks sat in a kind of scientific waiting room. What changed was not a conceptual breakthrough, but an industrial one. GPUs, originally built to render video game graphics, turned out to be almost perfectly suited for the matrix multiplication at the heart of neural network training. By 2012, a neural network called AlexNet, trained by Hinton's group at the University of Toronto, cut the image recognition error rate nearly in half at a major international benchmark. That moment is where the modern era starts. Think of it like this. Researchers had been building race cars for decades, but the engines were running on the wrong fuel. GPUs were the right fuel. The first thing most people get wrong about neural networks is what they actually store. When you imagine a system that can answer questions about history, science, cooking, and law, you probably imagine something like an encyclopedia, a giant database of facts, indexed and retrievable. That is not what a neural network is. A large language model like GPT-4 or Gemini 1.5 does not store a single sentence of text. What it stores is weights. Specifically, GPT-4 is estimated to have around 1.8 trillion parameters, each one a floating point number that represents the strength of a connection between 2 artificial neurons. There is no sentence about Napoleon stored anywhere. There is no fact about photosynthesis sitting in a row. What exists is a compressed statistical map of the relationships between concepts, extracted from reading roughly 1 trillion words of human text during training. When you ask a question about Napoleon, the network does not retrieve an answer. It reconstructs one by propagating your words through layers of arithmetic and generating the sequence of tokens most statistically coherent with both your input and everything the weights encode. The implication of this is profound. The network has no truth module. It has no fact-checker embedded inside it. What it has is a very sophisticated sense of what words tend to follow other words in context like the one you created. This is why hallucination is not a bug they forgot to fix. It is a structural feature of how the system works. Here is the part that should genuinely unsettle you. Neural networks do not process language the way you were probably told in any introduction you have read. The common explanation is that they learn word associations, like a very advanced autocomplete. That is approximately as accurate as saying a jet engine works by pushing air out the back. Technically not wrong, but misses everything that matters. What researchers discovered, particularly after the introduction of the transformer architecture by Google researchers in their 2017 paper Attention is All You Need, is that these networks develop something called attention heads. Each attention head is a mechanism that learns which parts of your input to weight more heavily when predicting each word of the output. A model like GPT-4 has around 96 layers, and each layer contains dozens of these attention heads operating in parallel. In 2022, researchers at Anthropic and separately at Future of AI ran interpretability experiments and found something genuinely strange. Individual attention heads appear to specialize. Some learn to track subject-verb agreement across long distances in a sentence. Others track whether a pronoun refers to a person or an object. Others appear to handle something closer to logical negation. In one famous experiment, researchers identified a circuit inside GPT-2 that, when activated, specifically retrieved the indirect object of a sentence, as in when you say John gave the book to Mary. A specific set of neurons activates to track that Mary is the recipient. That level of internal structure was not programmed. It emerged from training on text. The model is not mimicking language. It appears to be building internal representations of the grammatical and conceptual structure of language entirely on its own. 17 billion matrix multiplications, and something like grammar appears spontaneously. So what is actually happening step by step when you hit enter? Your text is first broken into tokens, which are roughly word chunks. The word unbelievable becomes 3 tokens. Each token is converted into a vector, a list of around 12,000 numbers, that positions it in a high-dimensional mathematical space where similar concepts sit near each other. King and queen are close in this space. Ice and cream are close in this space when the word cold has appeared nearby. Your entire question becomes a matrix, rows of vectors, which then flows forward through the model's layers. At each layer, attention mechanisms compute a score for every pair of tokens in your input, asking in mathematical terms how relevant is this word to that word right now. Those scores are used to create a weighted blend of the surrounding context for every single token simultaneously. This happens 96 times in succession in a large model, with each layer refining the representation. By the time your question has passed through all the layers, each token has been transformed by the full context of everything around it. The final layer produces a probability distribution over the model's entire vocabulary, typically 50,000 to 100,000 possible tokens. The model picks from the top of that distribution. Then it does this again and again, generating one token at a time, each new word feeding back in as part of the context for the next. The whole process for a single sentence of output happens in milliseconds because it is running across tens of thousands of GPU cores in parallel, each one handling a fraction of the matrix operations simultaneously. The complications are real, and they deserve to be stated without softening. The first is opacity. Despite the interpretability research that identified individual circuits, researchers still cannot reliably read out what a large model is doing when it produces a specific answer. A 2024 study by researchers at Harvard Medical School found that when GPT-4 made diagnostic errors in clinical scenarios, the errors did not cluster around rare diseases or unusual presentations. They clustered around confident-sounding mistakes on common conditions, exactly the profile most dangerous in a medical context. The second complication is resource concentration. Training a frontier model in 2026 costs somewhere between $100 million and $1 billion and requires energy equivalent to tens of thousands of homes running for months. This means the technology is not distributed. It is controlled by a small number of companies: Google, Microsoft, Anthropic, Meta, and xAI. That concentration is not neutral. It determines what values get trained into these systems, what languages and cultures are well represented in the training data, and who bears liability when something goes wrong. A federal judge right now is weighing whether AI-generated content constitutes protected speech. Nobody has a settled answer. The third complication is the alignment gap. The model has no goals. It optimizes for token prediction probability, not for being helpful or accurate. Helpfulness is approximated through a training step called RLHF, reinforcement learning from human feedback, where human raters score outputs. but raters prefer confident-sounding answers. So the model learned to sound confident. This touches your life more concretely than you might want to admit. If you are in law, medicine, finance, education, or any form of content work, you are already competing with outputs from systems that cost fractions of a cent per word and never sleep. The question is not whether to engage with this technology, but how to engage with it accurately. Knowing that these systems have no internal fact-checker should change how you use them today. You should not ask them to recall facts. You should use them to synthesize, structure, and draft, then verify the underlying claims independently. In healthcare specifically, hospitals in the United States and United Kingdom are actively deploying diagnostic support tools built on transformer architectures. If you interact with one of these as a patient, you now know enough to ask the right question. What training data was this model validated on? And does it include populations that look like me? In software development, code generation tools like GitHub Copilot produce code that compiles and runs, but often contains security vulnerabilities the model does not flag, because the model has no model of intent. It has patterns. By 2028, entry-level coding positions are expected to shrink significantly at major tech firms. Senior positions requiring system-level thinking are expected to grow. The mechanism you just learned explains why. What you have seen in the last few minutes is not a magic trick explained away, but something stranger. The numbers that power these systems were not written by anyone who understood what the final model